Hello, future engineers. Our lesson for today is about deflection methods. I will present one problem that will be solved in 7 available methods of computing deflections from theory of structures. So if you're still new to my YouTube channel, don't forget to subscribe so that I will be inspired to do more lecture videos that will be beneficial to your studies. Here we go. We have this problem. By 7 deflection methods, compute the slope and the deflection at points B and C. The value of EI is constant. So this is the given figure. It is a simply supported beam. So first, by double integration method, we solve for the reactions. So summation moment about D equals 0, clockwise as positive. So we have AY times 10. So of course AX 0. Minus 50 times 7 minus 20 times 4 times 2 equals 0. So solving for AY is 51 kilonewtons. Likewise, I will not show it anymore. R sub D is equal to 50 plus 20 times 4, 130 minus 51. So R sub D is 79 kilonewtons upward. So we section this last segment of the beam so that we can write our moment equations. So EI y double prime is equal to AY, which is 51 times x, minus 50 times quantity x minus 3, this is x minus 3, minus 20 times x minus 6 times x minus 2. So 20 times x minus 6 times x minus 2 is 10 times x minus 6 quantity square. So again, minus 20 times x minus 6 times x minus 6 over 2 is 10 times x minus 6 quantity square. So call that equation A. Integrating once, so we have 25.5 x squared minus 25 quantity x minus 3 square minus 10 thirds x minus 6 quantity cube plus c sub 1. Remember that c sub 1 is the slope at the origin, which is point A. Then integrating again, EI y equals 8.5 x cubed minus 25 over 3 x minus 3 cubed minus 5 over 6 x minus 6 to the fourth plus c sub 1x. There is no c sub 2 because c sub 2 is the deflection at A, and since it is the origin, then deflection is 0. Boundary conditions: when x is 10, y is 0, so we can solve the value of c sub 1. So 0 equals 8.5 10 cubed minus 25 times 7 cubed over 3 minus 5 over 6 4 to the fourth plus c sub 1 times 10. Solving for c sub 1 equals negative 3257 over 6. Remember, that's the slope at A divided by EI, of course. Now we can set x equals 3 and solve for slopes and deflection at B. So when x is 3, substitute in equation B. So 25 EI theta B equals 25.5 times 3 squared. This is 0. This is ignored because the value inside the parenthesis is negative. Then plus c sub 1, negative 3257 over 6. So theta B is equal to negative 313.33 over EI in decimal and in 3 decimal places. Then into equation C, EI delta B equals 8.53 cube, 0, ignore, minus 3257 over 6 times 3. So delta B is equal to negative 1399 over EI. So obviously it is negative, it is below the x-axis, the deflection at B. Then at C, x is 6 into equation B, then into equation C. So EI theta C equals 25.5 times 6 square minus 25 times 3 square, 0, then minus 3257 over 6. So theta C is equal to 150.167 over EI. Then into equation C, EI delta C equals 8.5 times 6 cube minus 25 times 3 cube over 3, 0 plus minus 3257 over 6 times 6. So delta C is equal to negative 1646 over EI. So that's it for the first method. Let's proceed to the second method by area moment method. So let's select D as our moment center, although you can select C as moment center, B, or anywhere. But the simpler moment diagram by parts would be making C or D as moment center. So I select D as the moment center. So remember, these are the reactions. So we have 51 times 10 is 510 over EI here. Then this is 50 times 7, 350 over EI. 20 times 4 times 2 is 160 over EI. By the way, this is 50 times C, so 150 over EI. And this is 160 over EI, second degree. Then the value here is 51 times 3, 153 over EI. That's the expected elastic curve. This is the tangent at A. So this is deviation of D relative to A. And if that's correct, then we expect this deviation of D relative to A as positive. So area of triangle, 1/2 of 10 or 0.5 of 10 times 510 times 10/3 moment arm. Then minus quantity 0.5 of 7 times 350 times 7 over 3 moment arm. Then minus 1/3 of 4 times 160 times 4 over 4 or 1, the moment arm. So deviation of D relative to A is equal to positive 16285 over 3 EI. Now that we have found it, then we can compute this values, call this HB, this one as H sub C, by similar triangles, or the other way is usual for theta A, which is negative. It is negative of deviation of D relative to A divided by 10. So by similar triangles, by the way, this very small division of B relative to A. So that's division of B relative to A. Then this is division of this is theta between A and B. From the figure, it is counterclockwise, so it is expected positive. The area between A and B, which is theta AB, of course, it is positive. Then we have a line, horizontal line, through this point on the elastic curve, so that the tangent at B from the horizontal line is clockwise, so it is expected negative. Theta B is expected negative. And this is the tangent at C. This is the tangent at A to the tangent at C, so the rotation is counterclockwise, so of course it is expected positive. It is equal to the area between A and C, areas between A and C. Then the horizontal line through the point on the elastic curve at C, then if the rotation from this horizontal line to the tangent at C is counterclockwise, then theta C is expected positive. So this is delta B, and this is delta C. This is deviation of C relative to A. This is delta C, this vertical distance. So from the figure, HB over 3 equals H sub C over 6 equals division of D relative to A as to 10. So 16285 over 3 EI over 10. So H sub B is equal to 1628.5 over EI. Then H sub C is equal to 3257 over EI. So from the figure, take note that delta B is negative. If you just treat them as positive first, but in the final calculation, you just put a negative sign, delta B plus deviation of B relative to A equals H sub B. That should be the equation. So this is 153 over EI, 51 times 3. This is 51 times 6, so 306 over EI. So EI theta EB is 1/2 of 3 times 153. So that theta EB is positive 229.5 as expected, because the rotation is counterclockwise. And theta A is bigger in magnitude than theta AB, so therefore theta B is negative because theta A is negative. Take note, it's below the positive x-axis, theta A. So from the figure, theta A is negative 1 over 10 of division of D relative to A. So it is equal to negative 3257 over 6 EI, which checks the value of C sub 1 in the double integration method. Then theta B is negative of absolute value of theta A minus absolute value of theta AB, which is 229.5 over EI. So it is expected negative, so theta B is negative 313.333 over EI as before. Then delta B, EI division of B relative to A, is moment of this area, 0.5 of 3 times 153 over EI times 2/3 of 3 is, 1/3 of 3 is 1. We sum up moment about B. So deviation of B relative to A is expected positive because point B on the elastic curve is above the reference tangent. So it is also 229.5 over EI. So from the figure, EI delta B equals negative because it is below the x-axis, and it is equal to the absolute value, negative of quantity absolute value of HB minus absolute value of deviation of B relative to A. So delta B is negative 1399 over EI as before. Then at C, EI division of C relative to A is equal to 1/2 of 6 times 306 over EI times 2 minus 1/2 of 3 times 150 over EI times 1. Summation moment about C. So division of C relative to A is positive 1611 over EI. Then theta AC, EI theta EC is 1/2 of 6 times 306 minus 1/2 of 3 times 150. So theta EC is equal to 693 over EI. Now let's solve for theta C first. So take note, theta AC is greater than theta A. So this is supposedly theta A, 3257 over 6. Then theta EC is bigger in magnitude, therefore theta C is positive, and it is positive absolute value of theta EC minus absolute value of theta A. So theta C is positive of absolute value of theta EC minus absolute value of theta A. So theta C is 150.167 over EI as before. And finally, from the figure, delta C is negative, so it is the negative of quantity absolute value of H sub C minus absolute value of deviation of C relative to A. So negative absolute value of H sub C minus absolute value of deviation of C relative to A, which is 1611. So delta C is negative 1646 over EI as before. Okay, let's proceed to solution number 3 by conjugate B method. So we already drew the moment diagram by parts with moment center at D from area moment theorems, and then let's use that moment area by parts. Then since this is simply supported and n supported, the equivalent conjugate beam will be the same. So pin at A, then roller at D. So we treat this as the loading by principle. So first, let's solve for theta A. That's the positive direction of theta A assumption. That's the shear, as well as at D going down. So summation moment about D equals 0, clockwise as positive. So we have theta A times 10 plus 1/2 of 10 times 510 times 10 over 3. Then minus 1/2 or 0.5 of 7 times 350 over EI times 7 over 3, then minus 1/3 of 4 times 160 over EI times 4 over 4 or 1, then equals 0. So solving for theta A is negative 3257 over 6 EI, just like before. Now let's consider AB. Positive theta for AB is theta B is going down because it is right section, and the positive moment or positive deflection is counterclockwise. So first, summation forces y, considering AB only. So theta A, which is negative 3257 over 6 EI plus 1 half of 3 times 153 over EI minus theta B equals 0. So solving for theta B is negative 313.33 over EI. Then summation moment about B equals 0, clockwise as positive, so negative 3257 over 6 EI times 3, then plus 1 half of 3 times 153 over EI times 1, then minus delta B equals 0. Solving for delta B is negative 1399 over EI as before. Next, we remove theta B and delta B so that you won't be confused. Let's consider AC and apply the positive direction for theta C and positive moment or positive deflection at delta C. First, summation forces y equals 0. So theta A plus 1 half of 6 times 306 over EI minus 1 half of 3 or 0.5 of 3 times 150 over EI minus theta C equals 0. Solving for theta C is equal to 150.167 over EI. Then summation moment about C equals 0, clockwise as positive. So negative 3257 over 6 EI times 6 plus 1 half or 0.5 of 6 times 306 over EI times 2. Then minus 1 half or 0.5 of 3 times 150 over EI times 1. Then minus delta C equals 0. So it's upward, so clockwise, downward, counterclockwise. So delta C is equal to negative 1646 over EI, just like before. Next, we proceed to solution number 4 by virtual work method. So remember the reactions. Then we draw another beam for the positive assumption of unit rotation at B, which is counterclockwise. So we have 1, 2, 3 segments. So for this method, let's just have our X from A, from B, and from C. Then we notice that if we continue, so if we make X from C, it's long. So that's why for the next method by Castigliano's second theorem, we change that section instead from C to any section in this 4-meter segment. So we proceed from D to the section CD. Same is true for our sectioning for the beam subjected to unit load. So this is the same segment, same sectioning. So due to this unit couple, if we sum up moment about D, so reaction at A times 10 equals 1. Clockwise, reaction times 10 equals 1. So therefore, the reaction here is upward, and it is equal to 1 over 10 or 0.1. Summation versus Y, so reaction at D is 0.1, also downward. So remember the guide, 1 times theta equals summation of integral 0 to L of Mamma Mia, where small m here is the moment at the section due to this unit couple here, while capital M is the moment at the section due to the actual loadings. Then over EI dx. Then for deflection, 1 times delta equals summation integral 0 to L Mamma Mia. So capital M, small m dx over EI. These big M's here will be the same. They only change for the smaller m because this is due to couple load and this is due to unit load. So we always assume that the couple application of the unit couple, unit load or virtual forces will be always positive, so that the result is final. So if it is positive, it's really positive. If it is negative, it means it's negative, or clockwise rotation or downward deflection. So EI times 1 times theta B, so we put EI there because EI is constant. So integral of the moment in this section is 51 times x, clockwise positive, remember, if you start from the left. So 51x for the small m, 0.1 times x dx, 0 to 3. For the next section, we have plus integral of 51 times 3 plus x minus 50x for the big moment. Then for the small moment, 0.1 times 3 plus x minus 1. So that's it, dx. Then for the last section, we have plus integral 51 times 6 plus x minus 50 times 3 plus x minus 10x squared, or 20 times x over 2. So minus 10x squared. Then for the small moment, it is 0.1 times 6 plus x minus 1 only, dx. So I will not show the detailed solution to this integration here. It's a waste of time. This is not integral calculus, so it is assumed that you have a calculator 991ES, 991MS, where it is able to evaluate integrals, or you evaluate this manually by simplifying first inside terms, then verify the following results. So the first integral is 45.9, the second is negative 254.7, the third is negative 1568 over 15. So combining, theta b is equal to negative 313.333 over EI as before. So likewise, we change the loading here by upward virtual force of 1 unit. Then we have the reaction here would be going down, because the moment of 1 about D is clockwise, then this should be downward so that it is counterclockwise. So it is 1 times 7, or reaction at A downward times 10 equals 1 times 7. Therefore, 7 over 10 is 0.7. Similarly, reaction at D would be 0.3 downward to balance. So same sectioning as before. Then EI delta B equals integral 0 to 3 of 51x as before. Then here this time is negative 0.7 times x, because this is now clockwise. Then plus integral of 51 times 3 plus x, you copy before, minus 50x, then times negative 0.7x times 3 times negative 0.7 times 3 plus x, the moment arm, then plus 1 times x, or simply x dx. Then for the last section, 51 times quantity 6 plus x minus 50 times 3 plus x minus 10x squared, then times the quantity negative 0.7 times 6 plus x minus 1 times quantity 3 plus x dx. So as before, I do not present the details of this integration, so I'll just give you the value. We have negative 321.3, the second integral is negative 764.1, and the third integral is negative 313.6. Combining, delta B is negative 1399 over EI as before. And finally, we have unit couple at C. Then reaction at A times 10 equals 1. So again, this is 0.1 upward. Then at D, 0.1 downward. Then EI times quantity 1 times theta C, same segment, equals integral of quantity 51x times 0.1x dx plus integral of 51 times 3 plus x minus 50x times quantity 0.1 times 3 plus x dx. Then the last is integral from 0 to 4 of quantity 51 times 6 plus x minus 50 times 3 plus x minus 10x squared. Then for the small moment, integral of times quantity 0.1 of 6 plus x, then minus 1 dx, because it is this section here. Again, the value of the first integral is equal to 45.9. The second integral is 208.8. The last integral is negative 1568 over 15. So combining, theta C is positive 150.167 over EI as before. And finally, we apply a unit upward load at C. And the reaction here is 1 times 4 divided by 10, so 0.4 downward. Then here it's 0.6 downward. So same sectioning, EI 1 times delta C equals integral 0 to 3 of 51x times 0.4x dx. So take note, same sectioning as above. Then plus integral of from 0 to 3, 51 3 plus x minus 50x times negative 0.4 times 3 plus x dx, 0 to 3. Then plus integral 0 to 4 of quantity 51 times 6 plus x minus 53 plus x minus 10x squared times negative 0.4 times 6 plus x, negative 0.4 times 6 plus x, then plus 1 times x. So the sectioning is the same as above. Then the value of the first integral is negative 183.6, the second is negative 835.2, the third is negative 627.2. So combining, delta C is negative 1646 over EI as before. So that's it for virtual work method. So next, solution number 5, Castellanos' second theorem. So this is almost the same as the virtual work method. Instead of applying unit virtual load, we apply actual load but assumed loading, invented loading. So first, we have to apply a couple at D. So remember that the reaction here is equal to 50. So due to the 51 upward, so due to the couple, reaction at A times 10 equals couple. So therefore, the new reaction at A is 51 plus 0.1 of the couple, or 1/10 of C. Then similarly here, it's 79 minus 0.1 of C. So same sectioning as before. And at C also, same sectioning. So we have EI theta B is equal to summation integral 0 to L of moment, partial of moment with respect to the couple, then dx over EI. Then for delta, or deflection, the same, but we have M integral 0 to L, M, partial of that moment with respect to the load P, then over EI. So EI theta B equals integral 0 to 3 of 51 plus 0.1 C times X. Then the partial derivative of this moment equation with respect to C is, you just remove C, then we have 0.1 X. Then plus integral 0 to 3 of quantity 51 plus 0.1 C times 3 plus X, moment arm, then minus 50X minus C. So in this section here, then the derivative of this moment is 0.1 times 3 plus x. Just imagine you differentiate this with respect to C. So remove C, 0.1 times 3 plus x, then minus 1. Derivative of negative C is negative 1 dx. Then plus integral 0 to 4 of 51 times 0.1 up 51 plus 0.1 of C times quantity 6 plus x minus 50 times 3 plus x minus the couple, and minus 10 times x squared, or 20 times x over 2. Then the derivative of partial derivative of this moment equation with respect to C is 0.1 times 6 plus x minus 1 dx. So prior to integration, remember you have to set the value of C, which is just invented, so it's 0. C is 0. So notice that 51x times 0.1x is same term as in virtual work method. The second term, 51 times 3 plus x minus 50x times quantity 0.1 of 3 plus x minus 1 is the same term as in virtual work method. Then the last, integral 0 to 4 quantity 51 times 6 plus x minus 50 times 3 plus x minus 10x squared close times quantity 0.1 times 6 plus x minus 1 is the same term as in virtual work method. So therefore, the answer is the same. Negative 313.333 over EI. Then for deflection, so we remove the reactions. We change the load, upward load P. So the reaction here would become 51, so P times 7 divided by 10, so minus 0.7 P. 51 minus 0.7 P. On the other end, it should be 51 minus 0.3, 79 rather, minus 0.3 P. So we have EI delta B equals integral 0 to 3 of 51 minus 0.7p times x. The derivative of the equation is negative 0.7x dx plus integral 0 to 3 of 51 minus 0.7p times 3 plus x plus px minus 50x. So we have plus px here. The derivative is negative 0.7 times 3 plus x, derivative px is x, or 1x. Then the last term, so we have to change because the equation is very long. So we make x start from d, and the result is the same. So it will be integral from 0 to 4 of 79 minus 0.3p of quantity x minus 10x squared, then minus times the derivative is negative 0.3x. So which is that? So 79, quantity 79 minus 0.6p times x, then minus the moment of this load, which is 20 times x times 6 over 2, or minus 10x squared. Then the derivative of this equation with respect to p is negative 0.3x. So evaluating, but before that we set the value of p equal to 0 because it is just invented prior to integration. So notice that this term here is same as in virtual work method. So the answer is negative 321.3. This one is 51 plus x minus 50x, then quantity negative 0.7 times 3 plus x dx, same as virtual work method. So the result is negative 764.1. So this is the new term, but we expect the same results. So if you evaluate the integral of that, it is also negative 313.6. So combining EI delta B, or delta B is negative 1399 over EI as before. Then next, we remove the reactions and loads and replace it by couple at C. So the new reaction here is 51. So due to the couple alone, reaction times 10 equals couple. So couple divided by 10 is 0.1 C. So this is 51 plus 0.1 C. On the other end, 79 minus 0.1 C. So EI theta C equals integral 0 to 3 of 51 plus 0.1 C x times derivative is 0.1 x dx. The moment here is 51 plus 0.1 C quantity x. So the differential or derivative is 0.1 x dx. Plus integral 0 to 3 of quantity 51 plus 0.1 C times 3 plus x minus 50x. Derivative is 0.1 times 3 plus x dx. Then plus the third term, integral of quantity 79 minus 0.1 C times x minus 10x squared. The derivative is negative 0.1 x dx. So setting the value of C to 0 prior to integration. So the first is similar to the expression from virtual work, 45.9. Second term, 208.8, similar also. This is the new term, but expect the same result of negative 1568 over 15. So combining theta C is 150.167 over EI, just like before. Then finally, we remove the loads and the reactions, replace it with an upward force at C, then this will be the result. So the due to P, the reaction here is downward, so it's negative. So it is P times 4 divided by 10. So you have to subtract 4 over 10 of P, or negative 0.4 P. Reaction at the right is 79 minus 0.6 P. So EI delta B equals integral of quantity 51 minus 0.4 P times x, then derivative negative 0.4 x dx, plus integral of quantity 51 minus 0.4 of P times 3 plus x minus 50x, then the derivative is negative 0.4 of quantity 3 plus x. Then at the rightmost, plus integral 0 to 4 of quantity 79 minus 0.6 P times x minus 10x squared, derivative is negative 0.6 x dx. So the value of the first integral, before we evaluate, you have to set P equals 0, so it's negative 183.6, same as before. This one is same as before in the virtual work method. And here, this is the new, so if we evaluate this, this gives us negative 627.2, which is the same as the value of the integral when we set x at the last section from C. So combining delta C is equal to negative 1646 over EI. So that's it. Let's have solution number 6 by three moment equations. So moment at B is 51 times 3, 153 kilonewton meter. This is moment BC. But moment BA, because is negative of 153. Moment at C is 51 times 6 minus 50 times 3. Or you may look at the moment diagram by parts, then look at the net moment there. So it is 156 kilonewton meter. Moment at A and moment at D are all zeros. So apply three moment equation in span A, B, D. So we select A, B, and D so that we have the same vertical distance from the horizontal line through the elastic curve at B. HA and HD will be the same, and they are equal to the deflection at B. So that's the elastic curve. This is the horizontal line through point B on the elastic curve. This is now the position of B. Then this is HA supposedly. Then this is deflection at B. And we have H sub D. So HD, HA are equal to delta B. So, but delta B is supposedly negative, but HA and HD are positive in this configuration because they are above the horizontal line. A and D are above this horizontal line. Our reference is the horizontal line at B. So this is the moment diagram by parts for the portion BD. So we compute the moment because we assume that B and D is a simply supported beam. We imagine there is a support here. So with 50 is ignored. It cannot affect the moment because B is a support in the assumption of the three moment equation. So this is the moment of the supposedly reaction at B due to this load here. But it is first, we need to compute the moment of the 20 kilonewton first. With the second degree, 20 times 4 times 2, 160 before we put this 160 kilonewton meter there. So because this is 160, that should also be 160 because the moment at D is 0 because that's a roller support, simply supported support. So moment A, LAB plus 2MB times LAB plus LBD plus MD rather, LBD plus 6A1A over LAB plus 6A2B over LBD equals 6EI times HA over LAB plus H sub D over LBD. So that's the form of the three moment equation. So I hope that you're already through with your three moment equations, or you have touched this subject in your theory of structure subject. MA0, so we begin with 2 times 153 times quantity 3 plus 7 plus 0. Then this is because AB, there is no load in between A and B. Remember, A and B are imagined to be simple supports. So there's this load 50, the support cannot bend the beam. So there is no value for 6A1 over A. For 6A2B, then we have to use the integral formula, 6 over 7, 6 over 7. So 6 over length BD is 6 over 7. Then area 2, we have two areas here. One is positive, the other is negative. So area 2B means the moment of this area with respect to the right end. So the first area is positive, so 1/2 or 0.5 times 7 times 160. Then the moment arm is 7 over 3. The second area is 1/3 second degree, so 1/3 of 4 times 160. The moment arm is 4 over 4 or 1. Then equals 6EI times HA over 3 plus HA over 7 because HA equals HD because they are reckoned from the horizontal line through B, and A and B are supports that do not move. So that's why HA equals HD. So I'll replace HD with HA. Then solving for HA, HA is positive 1399 over EI above because it is above the horizontal line through B. But the deflection is reckoned from the x-axis, and the x-axis is the line through the neutral axis of the beam through AD. So therefore delta B is negative. So we just put the sign negative, which is the same as before. Now for the second part, delta C, so this is the line through point C, horizontal line through point C. So again, we call this HA, and we call this H sub D. So we write three-moment equation for portion ACD, this line, and this is the deflection at C, which is equal to HA supposedly with respect to this horizontal line, the lower horizontal line through C, and H sub D is also delta C supposedly, which is also equal to HA supposedly. So take note that we have moment at C equal to 156. So applying the three-moment equation, so first term is 0, the second term is 2 times 156 times quantity 6 plus 4. So AC is 6, CD is 4. Then plus moment at D, which is 0, plus 6E1A over L1. So in beam AC, there is a load at the center. So the formula for concentrated load for 6A1A over L1 is PA, or 50 times 3 over L over 6 times quantity L square minus A square. So times quantity 6 square minus 3 square. So again, it is 50 times 3 over 6 times 6 square minus 3 square. Then for portion CD, the value of 6A2B over LCD is equal to, there's a formula for this, WL cube over 4. So 20 times 4 cube over 4. So that's the value formula from three-moment equation. Then equals 6EI. Instead of 6EI, by our experience here, because delta C is also negative, so we just make this negative. Then instead of HA and HD, which are also equal, I replace them with delta C immediately. So negative 6EI, quantity delta C over 6 plus delta C over 4. So the only unknown here is delta C. Solving for delta C is negative 1646 over EI. Now, how about for the slope? So we draw a tangent line at the elastic curve at point B. So it is here, green. I hope you can clearly see it. Then if that is the case, then the distance of point A from this reference tangent is the division of A relative to the tangent at B. And because this is the tangent at B, the angle that the tangent makes with the horizontal is the slope of B. So if this is true, then theta B is negative because the tangent is rotating clockwise from the horizontal, right? So theta B is negative. And the intersection of this horizontal line and the tangent line is, because this is a right triangle, tangent of theta B is equal to theta B itself. So it is equal to, theta B is opposite over adjacent 3. So therefore, this is 3 times theta B. So take note that theta B is expected negative. So this is the moment diagram of the original of the whole system. So 350 over EI, then we have 160 over EI second degree curve here. Then this is 150, 50 times 3. This is 153, and this is 306 over EI. So this is 3 theta B, because tangent of theta B equals opposite, this is opposite over 3, so the opposite is 3 theta b, and this very small distance here between A and the reference tangent at B is deviation of A relative to B. So therefore, deviation of A relative to B plus 3 theta B, we just treat them as positive, equals HA supposedly. So, but we remember that theta B is negative, or HA, which is equal to delta B. So EI division of A relative to B is the moment of this area with respect to A. So 0.5 or 1/2 of 3 times 153 over EI. The moment arm is, with respect to A, is 2. 2/3 of 3 is 2. So that would be division of A relative to B, 459 over EI. Then equate absolute value of 3 theta B plus division of A relative to B equals delta B, or HA, and it is 3099 over EI. So we can now solve theta B. Then remember that it must be negative based on the figure. Now, why is it negative? Because division of A relative to B is less than delta B in magnitude. So that's the reason. So theta B is 940 over 3 EI, the exact value, but in decimal form, and you make it negative, it is negative 313.333 over EI as before. Then for tangent at C, so this is the tangent at C, and this is division of A relative to C, and it is expected to be greater than delta C. If it is greater than delta C, then its magnitude is greater than delta C, then it is below the horizontal line through C. So it extends here. So this is a right triangle, and this is supposedly the slope of at C, or theta C, this angle between the horizontal and this tangent line, which is colored green, dashed line. Then theta C is equal to opposite over 6. So therefore, this is 6 theta C. The whole of this is division of A relative to C. This is 6 theta C, that one, 6 theta C, and this is delta C. The remaining distance is delta C. So EI division of A relative to C is 1/2 of 6 times 306 over EI. The moment arm is 2/3 of 6 of 4. Then minus this area of this triangle. Moment of this triangle is 1/2 of 3 times 150. The moment arm is 2 plus 3, so 5. So 0.5 of 3 times 150 times 5. So division of A relative to C is 2547 over EI, which is positive because A is above the reference tangent. And secondly, 2547 over EI is greater than delta C in magnitude. So that's why this figure is correct, because division of A relative to C is longer than the absolute value of delta C. So that's why, because the tangent at C is inclined upward, then therefore theta C is positive. So from the figure, division of A relative to C equals delta C plus 6 theta C. So 6 theta C plus delta C, 1646 over EI, equals division of A relative to C. So theta C is positive 150.167 over EI, just like before. So that's it. So here is the last method, which is the slope deflection method. So this is the beam, and let's set up everything. Moment BC is 51 times C, so 153 kilonewton meter, but moment, that's moment BC, or B to D. While moment B to A, because this is the other way around, so it is negative 153 kilonewton meter. Likewise, moment C to D is equal to 51 times 6 minus 50 times 3, which was computed before. But moment C to A is negative 156. So this is the formula. Moment near is 2EI over L times quantity 2 theta near plus theta far minus 3 delta over L plus fixed moment near. If we consider the far end, if the far end has moment, or there is a specific value of the moment, but if the far end has 0 moment, then this is revised to 3EI over L times quantity theta near minus delta over L then plus fixed end moment near minus 1/2 fixed end moment far. So 3ei over L times theta near minus delta over L plus fixed end moment near minus 1/2 fixed end moment far. Remember that the sign convention for slope deflection equation is clockwise positive. So if the chord on the elastic curve rotates clockwise, just like A to B, because the deflected shape would be this one, so B will be here, so the chord rotates clockwise, so that's treated positive, but actually delta should be negative in the final answer. Likewise, AC, the chord is rotating clockwise, so that is positive delta in this slope deflection equation notation. Then fixed moment near, if A is near, the left point is near, then it is negative. It is negative because the sense is counterclockwise, so that's why it's negative. But if the point, the far end or the near end is in the right side, so the fixed moment there is positive, and vice versa. So again, if the point lies in the left side of the beam or the section in consideration, the fixed moment is negative, and if it lies in the right side, the fixed moment considered is positive because it is clockwise. Remember the negative fixed moment like that. So it is counterclockwise here, then clockwise here. So negative left, positive at the right. So that's the sign convention. So moment AB is 0, moment DA is 0 also. Moment BA is negative 153, the opposite of moment BC. Moment BA or AC is 0, while moment CA is negative 156 kilonewton meter. Because these are the two moments that we are going to set up. But before that, we want to know the slope at A. So we consider moment AD first. Then because we anticipate that there's no problem with this concentrated load because we can write the fixed end moment formula for this only for this loading, which is at a certain segment only of the beam. So we consider a strip. The P here is 20 dx, that the thickness is dx, and because the height is 20 kilonewton per meter, so it is 20 dx the P. So we will call this x, and this is 4 minus x. So 20 dx, this is 4 minus x. So 0 moment AD equals, because the far end has 0 moment, so we use the other formula, 3ei over L10, distance with AD, then theta A minus 3 times delta. Delta is 0 because A and D remains on the support, so the chord joining them is horizontal, so 0. Then fixed moment of 50 at A is negative because A is in the left side, so it is equal to negative 50 times 3, then square of this distance from D, which is 7 square, all over L square, 10 square. Then minus, we follow the same format, but in integral form, 0 to 4, the value of x varies from 0 to 4. 20 dx, the distance of the centroid, or the distance of P from left is 6 plus x, then its distance from the right is 4 minus x, so that's why 4 minus x is squared here, divided by 10 square. Then minus 1/2, so the fixed moment at the right end is positive. So minus 1/2 of positive 50 times 3 square. So you just interchange the squared term here, squared quantity. So 3 square, 7. 7 is now raised to 1 over 10 square. Then minus integral 1/2 integral 0 to 4 positive 20 dx, 6 plus x square, 4 minus x over 10 square. So simplifying, 0.3 EI, then this is negative 73.5. The next, this integral is negative 448 over 15. This is negative 15.75, and this integral here is negative 656 over 15, then equals 0. because the moment AD is 0. So from there, we can solve theta A equals 3257 over 6 EI clockwise. So this is clockwise because the sign convention for slope deflection is clockwise positive. But the actual value of theta is negative because the correct sign convention is counterclockwise positive. So in other words, this is negative as if theta is being asked, and we have to finalize our answer. Then we now consider AB. So moment AB is 0 and it is 2EI over 3. We use 2EI over 3 because there is moment at the far end which is B. So quantity 2 times theta A plus theta B minus 3 times delta B over L, which is 3. Then because there is no load between A and B, because we imagine this A and B are fixed and the load is at B fixed, it cannot produce moment when the load is at the fixed end. So we can set up the first equation because we equate this to 0 as theta B minus delta B equals 2 times 3257 over 6 is negative 3257 over 3 after we transpose it over EI, equation 1. Likewise, we set up MBA, and MBA is equal to negative 153, and it is equal to 3 EI over L this time, 3 EI over L because the far end A has 0 moment. Quantity theta B minus delta over L, or the delta B over 3. Then again, there's no moment in between, so plus 0 minus 1/2 of 0. Simplifying, theta B minus delta B over 3 is equal to negative 153 over EI. Then solving these two equations simultaneously, or subtract equation 1 from equation 2 or equation 2 from equation 1, then we can solve delta B, and after that substitute in equation 1, we can solve for theta B. So I will not go into details with that because that's algebra. That's only algebra. So theta B is equal to 940 over 3 EI. Because this is positive, it means clockwise. But the final answer is, because this is clockwise, it is negative. So theta B is decimal form is negative 313.333 over EI, and delta B is, because our assumption is AB rotates clockwise, so B is below, so delta B is negative 1399 over EI, just like before. Next, we consider AC. Moment AC is 0, and because there is moment at C, so we use 2 EI over L, so 2 EI over 6. Distance between AC is 6. 2 times theta A plus theta C minus 3 delta C over 6. Then fixed moment is negative 50 times 3 square over 6 square. That's the only fixed moment. And simplifying this, we have theta C over 3. Simplify first. Distribute this 2 over 6. So we have 3257 over 9 plus EI theta C over 3 minus EI delta C over 6. Because this is 1/3, distribute, so delta C over 6 minus 37.5. Simplifying, we have theta C over 3 minus delta C over 6 equals negative 5839 over 18 EI. Call that equation 3. Then moment CA, because moment at A is 0, so we use this other formula, 3 EI over 6, quantity theta C minus delta C over 6. Then plus, it is positive, 50 times 3 square over 6 minus 1/2 of negative, sa far end is left, so negative 53 square 3 over 6 square. So this is the only load we consider between A and C. So simplifying, MCA, negative 156 equals EI theta C over 2 minus EI delta C over 12. Then the combined value of this is positive, negative 1/2 of negative, so 56.25. Then simplifying, we have theta C over 2 minus delta C over 12 equals negative 212.25 over EI. So again, solving these two equations simultaneously, we have two equations into unknowns, linear equations, so that would be an easy job to compute for these two unknown variables. So theta c is negative 901 over 6 EI. So meaning to say it is counterclockwise, and counterclockwise is positive. And delta B is still downward because it is positive. So we assume that the chord AC still rotates clockwise, and clockwise is positive in slope deflection equation, but it is downward in reality. So final answer, theta C in decimal form is 150, theta C 150.167 EI because it is counterclockwise, and counterclockwise is positive. And delta B is negative 1646 over EI. And it is understood downward. So that's it for this 7-in-1 problem. And I hope that you learned something from this. And I'm sure some of you did not experience these types of solutions, that there are 7, actually the 7 methods can be employed in any beam problems. So that's all, and I hope that you enjoy watching. So okay, let's have the matrix method. This is solution 8 to our problem. So first we consider AB and CD. Consider the whole system first and consider AB as one beam so that we can compute theta A and theta D. So we have the fixed moment direction, fixed moment direction. So let's consider a strip, and we have 20 dx. So let's choose this as our x from C. So fixed moment AD is equal to 50 times 3 times 7 square over 10 square plus integral of 20 times 6 plus x times 4 minus x quantity square divided by 10 square, 0 to 4. So combining the integral and this value here, the fixed moment AD is equal to 3101 over 30 kilonewton meter. Likewise, fixed moment dA is equal to 50 times 3 square, 7 over 10 square, plus integral 0 to 4, 20 dx, 6 plus x, quantity square, 4 minus x over 10 square. So combining again, we have fixed moment dA equals 3569 over 30 kilonewton meter. Then let's set up the matrix equation. So we have already the forces. The vertical forces or reactions are not important here. So let's just call it F1, then negative 3101 over 30 because this is counterclockwise. So the nodal force at A or at 2, because this is 1, 2 is clockwise and it is negative clockwise. And reaction here at D7 is not important because the displacement at D is 0. The vertical displacement at D is 0. Then the nodal load, which is opposite to this direction, is counterclockwise, and it is positive 3569 over 30. So this is the stiffness of member AB, 12 times EI, assume EI is 1, so we factor out EI, divided by 10 cubed, so 0.012, 6 times 1 over 6 over 10 square, 0.06, the negative of 0.012, then copy 0.06, then this is 6 over 6 EI over L square, so 0.06, 4 EI over 10, so 0.4, because EI is factored out. Then the negative of 0.06, then half of 0.4 is here. Then the third row is the negative of the first row. Then the fourth row is same as second row, except that second and fourth elements are interchanged position. So 0.2, then we have 0.4. Delta A is 0. Theta A is to be found. Theta D is 0 also, and theta D to be found. So therefore, we eliminate rows and columns associated with 0 displacements. So we expand rows 2 and 4 only, that one and that one. So we have negative 3101 over 30 and 3569 over 30 equals EI 0.4 0.2, 0.2, 0.4, theta A, theta D. Then supposedly plus 0.06, negative 0.06, then 0.06, negative 0.06 times 0, 0, but that is still 0, so we don't mind. So solving this equation for theta A and theta D, it's like 0.4 theta A plus 0.2 theta D equals negative 3101 over 30, and 0.2 theta A plus 0.4 theta D equals 3569 over 30. So theta A theta D is equal to 1 over EI times the inverse of this matrix times this force matrix here. And the result is we have theta A and theta D equals negative 3257 over 6 EI and 3413 over 6 EI. Next, we consider AB and BD because we want theta delta B and theta D. So since the force is at the fixed end, because we imagine that AB is fixed, so there will be no fixed end moment that will develop, only 50 kilonewton load, which is part of the load downward. And considering BD, so this is BD, we call this FBR, then the moment is to be computed by integration. Then this is moment at the right end, moment BB, and this is the force or reaction at D, which is not important because the displacement at D is 0. So first, fixed moment, we consider a strip. So this is 20 dx again, then this is x, and therefore fixed moment BD is equal to integral of 20 dx times 3 plus x times 4 minus x quantity square over 7 square. So that's the only thing, because 50 is acting at the fixed end. It has no contribution to fixed end moment, but it is considered part of the vertical load later. So it is equal to 5120 over 147 kilonewton meter. Then fixed end moment dB is same integral, except that 3 plus x is now square, 4 minus x is raised to 1 divided by 7 square. So it is equal to 9440 over 147 kilonewton meter. So let's solve for this FBR, because this is added as part of the 50 kilonewton load at joint B. So summation moment about D equals 0. So FBR times 7 plus this moment here, 9440 over 147 equals 5120 over 47 plus 20 times 4 times 2. So solving for FBR, it is equal to 18.659 kilonewtons. Then therefore, the moment or the nodal loads at B, which is marked 3 and 4, would be F3 is 50 plus, because FBR should be applied opposite to the fixed end force. That's the nodal force. So 50 plus 18.659 is 68.659 downward. And the moment or nodal load as rotation is opposite to this, which is 5120 over 147, and that's clockwise or negative. So that's the load there. At A, there is no moment here because as I said, the 50 kilonewton load is imagined to be acting on a fixed end, because we treat A and B as AB as fixed end, as well as B and B perfectly restrained beam. So KAB is equal to 12 over 3 cube, and that is 4 over 9, 6 EI constant over 6 over 3 square is 2/3, then the negative of the first, then copy the second, then 6 EI 1 over 3 square is 2/3, then this is 4 times 1 over 3 over L, 4 EI over L. This is the negative of 2/3, then this is 1/2 of 4/3. Then the third row is the negative of the first row, The fourth row is same as second row, except that we interchange the second and the fourth elements like that. So that is KAB. And KAB is 1, 2, 3, 4. So 1, 2, 3, 4 also. Then we have to establish KCD. So KBD rather. So we have 12 over 7 cube. 12 EI is factor out over 7 cubes, so 12 over 340. 6 over 7 square is 6 over 49. The negative of the first term, then copy the second term. Then this is 6 over 7 square, 6 EI over 7 square, so 6 over 49. 4 EI 1 over 7, so 4 over 7. The negative of 6 over 49 and 1/2 of 4 over 7 is 2 over 7. Then the negative of the first row, then copy the second row, except that we interchange second and fourth row elements of second and fourth column elements. And that is the stiffness of BD, which is BD is 3478. So 3478. Then the forces, remember the nodal force at A is 0, at B negative 68 point something, 68.659. Then at the moment is clockwise, so negative 5120 over 147. Then at 8 or at D, the moment or the nodal force there is counterclockwise, positive 9440 over 147. So this is this is 2, 3, 4, 8. So the numbering is 2, 3, 4, 8. 2, 3, 4, 8. Then this is 2, 3, 4, 8 vertically. So we have to consider 2, 2. So 2, 2 is 4/3. It's in the preceding slides. This is 3, 2, and 3, 2 is negative 2/3 in the preceding slides. 4, 2 is 2/3 in the preceding slides, and 8, 2, there's no 8, 2, so 0. Then this is same as this. We copy by symmetry. It's 0. Then this is 3, 3. 3, 3 is 12 over 343 plus 3, 3 in the preceding slide, so 1480 over 3087. This is 4, 3, which is 4, 3, 6 over 49, then plus the value of 4, 3 in the preceding slide, so negative 80 over 147. Then this is 8, 3. 8, 3 is 6 over 49. There's no 8, 3 in the preceding slides. So 6 over 49, then we copy negative 80 over 147 and 6 over 49 here. So this is 4, 4. 4, 4 is 6 over 49 plus 4, 4 in the preceding slides. It's, I think, 4/3, so that's why you have 40 over 21. And this is 8, 4. 8, 4 is 2 over 7. This is the only 8, 4 here. There's no 8, 4 in the preceding slide. So 2 over 7, then copy 2 over 7. Then finally 8, 8 is 4 over 7. Then theta A is negative 3257 over 6, solved in the preceding slides. And we don't know delta B and theta B. And this is theta D. So we expand this row here. So, or we eliminate rows and columns associated with, or we simply expand this because we know the displacements at A and at D. So expanding, we have negative 68.659, then negative 5120 over 147, then 1480 3087 EI, negative 80 over 147, negative 80 over 147, 40 over 21 times theta B, delta B and theta B, then plus, we have the other 2 by 2 matrix, negative 2/3, 6 over 49, 2/3, 2 over 7 times this known displacements, negative 3257 over 6 EI and 3413 over 6 EI. So simplifying this value here, negative 2/3 times negative 3257 over 6 plus negative. So we have EI times negative 2/3 times negative 3257 over 6 EI, and plus 6 over 49 times 3413 over 6. So EI is cancelled. So we have, so we copy same matrix, then let's simplify this portion here. So the simplified portion here is negative 2/3 times negative 3257 over 6 plus 6 over 49 times 3413 over 6, which is 431.542, and 2/3 times negative 3257 over 6 plus 2 over 7 times 3413 over 6 is negative 199.365. So transposing this and combining with these values, so we have negative 500.201 and 164.535 equals EI 1483.87, negative 80 over 147, and we copy this 2 by 2 matrix, then times delta B, theta B. So solving for delta B and theta B, it is the inverse of this matrix divided by EI times this matrix here, or simply this is the first equation, 1483 over 3087 delta B minus 80 over 147 theta B equals negative 500.201, and negative 80 over 147 delta B plus 40 over 21 theta B equals 164.535. Solving the two equations simultaneously gives us this answer, which is the same as before, negative 1399 over EI for delta B, and for theta B, it is negative 313.333 over EI. Then finally, we consider AC and CD. So we have the stiffness for member AC is EI times 12 over 6 cube is 1 over 18, 6 over 6 square is 1 over 6, then the negative of 1 over 18, then copy 1 over 6, then 6 over 6 square is 1 over 6. This is 4 times 1 over 6, or 2/3. This is negative of 1 over 6, and this is, the next is 1/2 of 2/3 is 1/3. Then the negative of the first row, then copy the second row, except that we interchange the second and the fourth elements. So that's the stiffness of AC. So we are interested of ACD, so it is 2, 5, 6, 8. And but this is AC, so this is 1, 2, 5, 6, 1, 2, 5, 6. Meanwhile, the stiffness of CD is 12 over 4 cube, EI times 12 over 4 cube, or 3 over 16, 6 over 4 square is 3 over 8, then the negative of 3 over 16, then copy 3/8, then 6 over 4 square is 3/8. This is 4 times EI over L, 4 over 4 is 1, EI is factored out. Then this is the negative of 3/8, then half of 1 is 0.5. Then the negative of the first row, then copy the second row, except that we interchange the second and the fourth element. Second and the fourth element interchange. So this is 5, 6, 7, 8. This member CD here, 5, 6, 7, 8. So we only considered the nodes 2, 5, 6, and 8. So because of symmetry, we imagine that A is fixed and C is fixed. So half of 50 is 25, so that's also 25. The fixed moment here is 50 times 3 times t squared over 6 squared, and that would be 37.5. Same is true on the other side, 37.5. CD is also symmetrical with respect to its load. So the reaction here, or upward force, is 20 times 4 over 2. So that is 40. And here it's also 40, but not important. Then the moment here is 20 times 4 squared over 12 is 80 over 3. Same is true on the other side, but clockwise 80 over 3. So that the nodal force at C is opposite to this, at A is opposite to this, at 2. So it is clockwise 37.5 or negative 37.5. At C, we have 25 and 40, which is opposite. So downward, negative 65. So negative 37.5, negative 65. Then here it's the 65 over 6. The moment is 37.5 minus 80 over 3 is 65 over 6. Then here is the opposite of clockwise 80 over 3, so counterclockwise 80 over 3, so positive 80 over 3. Then we have here 2, 5, 6, 8. We need 2, 5, 6, 8. Vertically also 2, 5, 6, 8. So 2, 2, we have 2, 2 is 2/3 only. So 2/3. This is 5, 2, column 5, row 2, 5, 2, negative 1, 6. And there's no other 5, 2, negative 1, 6. 6, 2, 6, 2 is 1/3. So that's why it's 1/3 here. 8, 2 is 0 because there's no 8, 2 here. Then copy negative 1, 6, 1/3, and 0 because it is symmetrical. This is 5, 5. So 5, 5 is 1 over 18 and 3 over 16. 1 over 18 plus 3 over 16 is 35 over 1 over 4. This is 6, 5. So 6, 5 is negative 1 over 6 plus 1 plus 3/8. Negative 1, 6 plus 3/8 is 5 over 24. And this is 8, 5. 8, 5 is 3/8 only. Then copy 5 over 24 here and 3/8 here. And we have 6, 6. 6, 6 is 2/3 and 1. 2/3 plus 1 is 5/3. And this is 8 over 8, 6, column 8, row 6, 0.5. So 0.5, copy 0.5 here. Finally, 8, 8 is 1. So 1. Then we expand again the second and third rows. We expand. Then we have negative 65, 65 over 6 equals EI, 35 over 144, then 5 over 24, then 5 over 24, 5/3 times delta B, theta B, then plus EI times matrix negative 1, 6, 3/8, 1/3, 0.5 times this known displacements, negative 3, 2, 5, 7 over 6. So negative 65, 65 over 6 is this matrix here, the center matrix. Copy, then delta B, theta B, plus EI times matrix negative 1, 6, 3/8, 1/3, 0.5. Then we have negative 3, 2, 5, 7 over 6 EI and 3, 4, 1, 3 over 6 EI. So expanding this second term of this matrix, then we just copy the first two first. So negative 1, 6 times negative 3, 2, 5, 7 over 6 EI. So cancel EI. Then plus 3/8 times 3, 4, 1, 3 over 6. That's 303.785. And 1/3 times negative 3, 2, 5, 7 over 6 plus 0.5 of 3, 4, 1, 3 over 6 is 103.472. Finally, combine it with here. So negative 368.785 and 65 over 6 minus 103.472 is negative 92.639 equals EI. Then this 2 by 2 matrix times delta B, theta B, or consider this as the first equation, second equation. So solving these two equations simultaneously, or you may invert it as the inverse of this 2 by 2 matrix times this matrix here, force matrix, then we can compute the delta C, which is equal to 1646 over EI, and theta C rather is equal to 150.167 over EI, which is the same answer as before. So that's it, and I will no longer talk because the solution is very long. I hope that you're not tired of listening to my discussion.